Hi everyone, Ryan Jackson here. Hope you're doing well. Today we're going to cover section 250.122b, which is sizing the equipment grounding conductor when the ungrounded conductors of the circuit have been increased in size for voltage drop or other reasons. This is a rather controversial subject. It was first put into the code in 1975. And ever since the 90s, right up until present day, we've seen a lot of proposals and a lot of changes in this section to make it say what we want it to say. And I gotta be honest, I don't think the code is perfect as is in the 2020, but I also don't know how to make it perfect. And I'm not certain that we ever can. This is kind of a difficult subject because for some applications, it makes perfect sense. For other applications, it makes no sense whatsoever. So let's go ahead and take a dive into it and see what 250.122b has to say. Now, before we get into B, we kind of have to cover A first, because 250.122a talks about how to size the equipment grounding conductor in general. So for normal applications, 250.122a says that the equipment grounding conductors of the wire type must be sized using table 250.122, but they never need to be larger than the circuit conductors for the equipment. All right, pretty simple, to be perfectly honest. If I have a 20 amp circuit breaker or fuse, then I would use a 12 gauge copper equipment grounding conductor. By the way, nothing against aluminum or copper clad aluminum. I'm just going to be talking in copper today. So if I have a 15 amp breaker or fuse, I use 14 gauge copper for my equipment ground. If I have a 30 through 60 amp circuit breaker, I would use 10 gauge copper. So we size the equipment grounding conductor based off the rating of the circuit breaker or fuse that it needs to open. So when we think about sizing it, we need to understand why we install an equipment grounding conductor. Why do you put a green wire inside of your PVC conduit, for example, or inside of your MC cable? And the answer to that is to open a fuse or breaker in the event of a ground fault. So if I take the green wire and I ultimately connect it to the utility neutral, ultimately, and then I connect it to the metal parts of the service disconnect, and then I take the green wire and I connect it to all metal parts that are part of the electrical installation. That means if I have a ground fault, if the ungrounded conductor, a circuit conductor, energizes the metal parts, then it's essentially a short circuit. Then, I, for all intents and purposes, I'm taking the black wire and jamming it into the green wire, and that's going to have an extremely low impedance, and that's going to generate a lot of current, and it's going to trip the breaker or open the fuse. So as the rating of the circuit breaker or fuse gets higher and higher, it's going to take more and more current to open the overcurrent device, obviously. It takes a lot more current to open a 2,000 amp breaker than a 20 amp breaker. Now, how do I get those higher values of current? Well, I need to generate more fault current, which means I need to have a larger equipment grounding conductor, which has lower impedance and can generate high amounts of current to open the circuit protective device. So I size the equipment grounding conductor based on the breaker or fuse that it needs to open. And that's a fairly simple concept. The bigger the breaker, the bigger the wire. And I say breaker, but breaker or fuse, same concept. So 250.122a just says, listen, nice and easy. Figure out what size of breaker or fuse supplies the circuit, use the table, pull that size wire in your conduit, and you're good to go, right? So that's if I'm using an equipment ground of the wire type. You can still use a metal conduit as your equipment grounding conductor. You don't necessarily need a bare or green wire inside of your conduit if it's metal and it complies with 250.118. But for our discussion today, we're talking about sizing equipment grounding conductors of the wire type. So far it's nice and easy. I want to point out one little thing though. Notice that if I have a breaker or fuse that's rated 15 amps, I use a 14 gauge copper. And for 20 amp, I use 12 gauge copper. And for 30 amps, I use 10 gauge. That means that for a 15, 20, or 30 amp branch circuit, generally speaking, not talking about a motor or a feeder tap or anything, generally speaking, for a 15, 20, or 30 amp branch circuit, the equipment grounding conductor has to be the same size as the ungrounded conductor, right? For a 14 gauge, for a 15 amp circuit, I'm pulling 14 gauge ungrounded conductors, and I'm pulling a 14 gauge equipment grounding conductor. With a 20 amp, I'm using 12, 30 amp, I'm using 10. So we're going to do a little bit of math here in a minute, but I want to point out that for 15, 20, or 30 amp circuits, the math is going to be extremely easy. Just remember that the green wire has to be the same size as the black wire. Once we get to 35 amp circuits and greater, then we're going to have to do a little bit of math here when it comes to section 250.122b. What this rule says, and you can see that it was revised in the 2020, if the ungrounded conductors of a circuit, the hot conductors, are increased in size for any reason other than temperature correction or ampacity adjustment, then the equipment grounding conductor must be increased in proportion based on circular mill. All right, so I'm showing a parking lot here in the picture, and the reason that I'm doing that is, why would I increase the size of ungrounded conductors? Well, usually it's a voltage drop issue. And in fact, in 1975, when they put it into the code, all the way up to, I believe, 2002, it said that this only applies when you're increasing the size of your wire for voltage drop. And in reality, that's the most common application of this rule. So I want to just stick to voltage drop for right now. I've got a parking lot. It's got a long circuit. I increased the size of my conductors. That means I have to increase the size of my equipment ground in proportion, right? That's what this rule says. So I've got a 20 amp circuit for my lights. But because it's a very long circuit, I use 8 gauge ungrounded conductors instead of the 12 gauge, which would normally be permitted. All right, well, that is an increase in size. That means I need to increase the size of my equipment grounding conductor in proportion to the increase of the ungrounded conductors. Okay, so how am I going to figure out all of this? Well, you go to the code book. In the very back, you go to table 8 in chapter 9, and that gives you the circular mill of the different conductors. All right, let's go ahead and open the code book for a second. I went to my NFPA link page. That's the digital version of the code book. And I'm here under the 2020 NEC. We're going to click on that, open it up, go down to chapter 9, which is the tables. Table 8 is down here at the bottom. It's conductor properties. And that's where I'm going to find the circular mill area for my conductors. All right, so if I want to make this a little bit bigger, you can see that on the left, I've got the size of my conductors in American wire gauge or circular mill. I go down here to 12 gauge, and I figure out that the circular mill of a 12 gauge is 6,530. So I'm going to write that number down because that was my starting point. I increased the size of the ungrounded conductors from 6,530 circular mills to 8 gauge, which is 16,510. And you can see that that's a pretty substantial increase. We need to do a little bit of math and figure out how to get there. So let's bring back up the PowerPoint. 6,530 circular mills and 16,510 circular mills. So if I do the math, that is a 252% increase. So 16,510 divided by 6,530 is 252%. So the 12 gauge equipment grounding conductor needs to be increased by a factor of what? 252%. Okay, so I know that I start at a 12 gauge equipment ground for a 20 amp circuit, and I need to increase it by 252%. Okay, well, we know that 12 gauge is 6,530 circular mill. If we increase it by 252%, it's going to yield what? 16,510, which is an 8 gauge. And that's why I said earlier that for a 15, 20, or 30 amp branch circuit, the size of the equipment grounded conductor has to be the same size as the ungrounded conductor. Because if you increase one, you have to increase the other in proportion. And the starting proportion is 1:1, right? It's a 12 gauge hot, it's a 12 gauge equipment ground. If you increase both of them by a factor of 2.52, they're both going to yield the same number. So the math is easy for those circuits. If I don't have a 15, 20, or a 30 amp branch circuit, I actually might have to do a little bit of math. So here I've got a 40 amp circuit, and due to voltage drop, we used 2 gauge ungrounded conductors instead of the 8 gauge that would normally be permitted. So I have to do the same procedure. I would go back into table 8 in chapter 9. I would find the circular mill of my 8 gauge wire, which I could have used, but for the voltage drop, I find that circular mill and I write it down, 16,510. Then I find the circular mill of the conductors that I actually installed. 2 gauge conductors are 66,360. So then I would do the math, and I realized that that is an increase of 402%. All right, so write that number down, 402%. Then I'm going to find my required equipment grounding conductor. This is a 40 amp circuit, which means at a minimum I would use a 10 gauge equipment ground. But because I increased the size of the ungrounded conductors, I now have to increase the size of the equipment grounding conductor in proportion. So I'm going to find the circular mill of my 10 gauge, same table, 10,380 amps. I'm going to increase that by 402%, and that's going to result in a required circular mill area of 41,740 for my equipment grounding conductor. So let's go ahead and bring the code book back up. Make this a little bit bigger so we can see it. I need, 41,740. And as I scroll down, we can see that that would require a 4 gauge. And lucky us, the math worked out absolutely perfectly. So going from an 8 gauge to a 2 gauge actually yields the precise number needed. So that would be a 4 gauge equipment ground. The mistake that a lot of people will make is they'll say, okay, well, I increased from 8 gauge to 2 gauge, and that's an increase of 1, 2, 3, 4 conductor sizes. So I need to increase the equipment ground by 1, 2, 3, 4 conductor sizes. That's not a proportionate increase. Proportion means mathematically. So we do have to do this exercise anytime I increase the size of the ungrounded conductors for voltage drop. But I want to be clear on this. This is not just for voltage drop. Maybe I installed larger wires because that's all I had on my truck. I would have loved to install 8 gauge wires to this machine, but all I had was some 2 gauge wire. So that's what I installed. Now, that's not a voltage drop concern, but one thing that it will do is it will ultimately increase the amount of current that is delivered during a fault, right? If I increase the ungrounded conductors from 8 to 2, then I decrease the resistance, which increases the current during a fault. Now, normally we would say that's a good thing, right? We want breakers to trip faster and fuses to open faster during a fault, so there's nothing wrong with that, right? Well, to a certain extent, that's true. But how far can we get carried away here? What happens if I have like a 4-aught ungrounded conductor and I use a 12 gauge equipment grounding conductor? When I hit those two together, is the breaker going to trip? Well, probably, but there's also a decent chance that that 12 gauge copper conductor turns into molten copper. It's going to evaporate because of how much current it's subjected to for that short duration. So at some point, I do need to recognize that it doesn't matter why I increased the ungrounded conductors. I still have to increase the equipment grounding conductor in proportion. Now, if we look at the language again, it says if I increase them in size for any reason besides temperature correction or ampacity adjustment. Okay, so if I've got 6 conductors in a conduit, or if I'm installing my wires in a high ambient temperature, and I had to make them bigger, well, is that really an increase in size? No, that's actually the minimum that would be required, isn't it? If I had a 20 amp circuit, and I have, off the top of my head, I have 10 current carrying conductors inside of that conduit, I'm not going to be able to use 12 gauge, right? I'm going to have to apply an ampacity adjustment and might require 10 gauge conductors. So is that an increase in size? Well, No, it's not an increase because it's the minimum required to carry the load, right? So it's an increase in size mainly for voltage drop, but truthfully, any reason other than temperature correction or ampacity adjustment. Now, here's the problem. If this is for voltage drop, it makes perfect sense. Look, if you have so much voltage drop that you had to make the black wire bigger, you're going to have the same problem on the green wire, and you're going to have to make it bigger. Otherwise, we're not going to be able to generate enough current to initiate the overcurrent device in the event of a ground fault. So it makes perfect sense to increase it for voltage drop. But sometimes it doesn't make any sense at all. Let me give you an example. I've got an air conditioner, right? I'm roughing in a house. I'm a residential electrician or commercial. I'm wiring this house, and I don't know what size air conditioner the HVAC guy is going to install. So it's a fairly small house. I'm going to cover myself, and I'm going to say, you know what? I'm going to run 8-2 NM cable out to the air conditioner. And then I don't care what he installs, I'm covered because it ain't going to be more than 40 amps. So I run 8-2, and I'm in good shape. Now think about it. 8-gauge NM cable has 8-gauge ungrounded conductors and a 10-gauge equipment ground. Is that right? So for a 40-amp circuit, it works great. But now I come back to trim out the house. They've installed the air conditioner, and I realize that it's only a 30-amp unit. All right, well, my 8-gauge wire is larger than what's necessary for the load. Now, did I increase it in size? Well, not intentionally. And do I have a problem? I mean, if I put it on a 30-amp breaker, is that 8-gauge wire going to trip the breaker in the event of a ground fault? Sure, it's not a problem at all. But if you really want to read this section with a magnifying glass, it's a violation. Because a 30-amp circuit means that the size of the equipment ground has to be the same size as the ungrounded conductor. Right? Remember our example with the parking lot. So now we have an absurdity. Think about this for a second. You would have to rip out that wire and special order some wire if we wanted to use 8-gauge wire with an 8-gauge equipment ground. Or how else could you solve it? Well, maybe put it on a 40-amp breaker. Now, a 40-amp breaker requires more current to trip, so we're making the situation worse, but we're making it code compliant now. And then if I look at the nameplate on the air conditioner, though, it says, hey, maximum overcurrent device is 30 amps. So now I'm back to square one. And you can see all of these mental gymnastics for something that really doesn't matter, right? If we're not increasing it for voltage drop and we're not making a gross misapplication, this section probably isn't that big of a deal. So how do we write this rule? And by the way, for the 2020 code, this is such a problematic section. And like I said earlier, I think it's impossible to make this section perfect. So what they did for the 2020 code is there were so many proposals to change 250.122b, and the proposals, all of them solved different parts of the problem. None of them solved all of the problem. So Codemaking Panel 5, what they did is they said, look, obviously we have a problem. We need to fix 250.122b. How do we do it? What they ended up doing is they completely started over in all of 250.122. The whole fundamental concept of how we size equipment grounding conductors, they were going to revisit. So they said, you know what? Forget it. We are never going to size it off the breaker or fuse. That's not what we're going to do anymore. We're going to size the equipment ground based on the size of the ungrounded conductors that it's associated with. And they voted on it and they passed, and that was what was going to be in the code. They published that in what we call the first draft of the NEC, and that's where it's open for public review. And you can submit comments on the code changes. You can say, look, that's a good idea, keep doing it, or that's a bad idea, you should have done this or that. Well, a lot of people read what they did and lost their mind, myself included. And a lot of people submitted public comments saying, hang on. If we want to solve 250.122b, let's solve 250.122b. Let's not reinvent the entire scheme of grounding and bonding in the NEC. So the code change process worked exactly like it's supposed to. We make changes, the public reviews it, The public provides comments, and then we change the code based on those comments. At the end of the day, what they ended up doing is saying, look, we have no idea how to fix 250.122b and make it applicable for everything, because it might not even be possible. So we're going to keep sizing the things the way we always have, and then we're going to add this very interesting exception. It says, look, equipment grounding conductors, now this is only for size increases. This is just 250.122b. It's not the entire section. It says, look, equipment grounding conductors can now be sized by a qualified person, not even an engineer, but a qualified person, if they still provide an effective ground fault current path as required in 250.4a or 250.4b. Okay, so it's saying, look, at the end of the day, we need a safe installation. Right? That's what 250.4a and 250.4b both say. A for grounded systems, B for ungrounded. It says, listen, no matter what happens, we need a safe installation. So this is saying, as long as a qualified person can size it and ensure that it's going to have an effective ground fault current path, then let's let the qualified person do it. It doesn't even need to be an engineer. Now, that's a little bit surprising, because when it comes to sizing equipment grounding conductors outside of what the code gives us, you might think that we would have to start looking at damage curves and different things and figuring out impedances and all of that, and maybe that should require an engineer. But there's an interesting program that's free to download, and I want to be very clear on this. I'm not selling you anything. I don't make money from this, from the software that I'm going to talk about. But it's called GEMI or GEMI. And it was a software that was put together with research at the Georgia Technical Institute, if I'm not mistaken, at Georgia Tech. My late friend Richard Lloyd was very heavily involved in the creation of this. And what's awesome about it is it's free. So I'm going to put a link in the description, and it will show you how you can download this software. It's absolutely free, and it's pretty easy to use, and we're going to go ahead and do some examples. So using this software, I should be able to ensure that the breaker or fuse will open and result in a safe installation. So before we get to the software, we need to figure out, how does a breaker or fuse work? Well, generally speaking, they work on the concept of inverse time and current, which means the higher the current it's exposed to, the faster it's going to open, right? If I have a 20 amp breaker and I put 20 amps on it, it will never open. And that's by design. So looking at our graph here, time is vertical and current goes left to right. And I want to point out really quick, this is not per scale. This is a logarithmic scale. So what I mean by that is, if we wanted the same distance between the 1 and the 2 and the 2 and the 3 and the 4 and the 5, we'd have a 100-foot wide and a 100-foot tall piece of paper to do it. Okay, so this is done in a logarithmic scale. So the concept here is this. On the bottom, I have the rating of my breaker measured in multiples. So if I have a 20 amp breaker times 1, which is 20 amps, how fast will it open? Well, if I move up here, the answer is it never will, because it's not supposed to. It's rated 20 amps. If I put 2 times the rating, or 40 amps, how fast will 40 amps on a 20 amp circuit breaker open? If I follow this up, and these are all going to vary based on the breaker, but if I follow this up, it will open somewhere between 15 seconds and 2 minutes, give or take. That's at 40 amps. Now, is that good enough if I have a ground fault? If I have that metal lighting pole for my parking lot light, if it is energized to a ground fault, should that remain energized for up to 2 minutes? Probably not. I think we can all agree that we need the breaker to trip faster than that. So what if I put 5 times the rating of that circuit breaker, which would be 100 amps? Well, now we can see that we've left the thermal part of the breaker and we've gotten into the magnetic part of the breaker. And that's when it's going to open very quickly. So once I start putting 5 times the current rating or higher, you can see that the opening time is down here in the like 0.005 seconds range. And that, of course, is going to be what we're after. So that's what we're trying to do. We're trying to create large amounts of current to get the circuit breaker or fuse to open quickly. How do I do this in the field? How do I do this as a regular person? Well, that's where we're going to do an example, and we'll take a look at the software. This is the GEMI software, and again, I'll put a link down below as to how you can get it. If I want to figure out how long of a wire can I go and still ensure that I can trip the breaker. So in other words, I'm doing that parking lot. If I didn't want to have the same size equipment ground as the ungrounded conductors on a 20 amp circuit, because maybe it didn't make sense, maybe it's not for the parking lot, maybe it's for the air conditioner. Well, if I increased the size of the ungrounded conductors to 8 gauge, and I've got down here on the bottom right, I've got a 20 amp circuit breaker. If I want to generate 10 times the amount of current, right, to get 200 amps in order to make it trip quickly, if I had 8 gauge for my hot, and we used NM cable, and it has a 10 gauge equipment ground, I could use this program to calculate whether or not that's actually going to work. And according to the software, it says, listen, you can run it 236 feet, and you'll still be able to generate 200 amps to trip that overcurrent device. And we can play around with all the different values. Let's say I put it on a 30 amp overcurrent device. Then I could only run it 157 feet, which makes sense because I'd have to generate more current in order to trip the breaker quicker. So that is how I would figure out, using the qualified person and not necessarily an engineer, how to increase the size of the equipment grounding conductor when we've increased the ungrounded conductors for any reason besides temperature correction or ampacity adjustment. I know it's kind of a tricky subject for a lot of people, but at the end of the day, I don't know how we could make it easier in the code. I really don't. Some things in the code book are difficult because the topic is difficult, and I think this exception, it's rather surprising the first time you see it in the 2020 code, but I actually think it's a good exception. We can do some other things as well using the same software. What if I'm using just a metal conduit as my equipment grounding conductor? What if I'm just using EMT? No green wire in it. That's legal, right? Assuming we're not doing a swimming pool or healthcare, things like that. But how far can you run a piece of EMT before it has so much resistance that it will no longer be able to trip a breaker? I mean, different concept than the increasing in size thing that we were discussing, but kind of the same principle. We can calculate that. So up here is the allowable conduit length. If I'm running 8 gauge conductors and I've got a 40 amp circuit breaker, I could calculate. Let's see here. Conduit is not going to be PVC, is it? EMT, and we'll use 1 inch for that. I could run that 164 feet before I'd have to concern myself with running an equipment grounding conductor inside of it. All right, so there you go. You can go ahead and use a software like the GEMI software. And of course, there's other, more elaborate softwares out there, I'm sure, but this is a nice, easy, free one. And you can use it to size the equipment grounding conductor when you're increasing in size for voltage drop or other reasons other than temperature correction or adjustment factors. So a rather surprising allowance, but I think it's a good allowance. Again, I'm not saying that it's perfect, but I think it's better than anything that we've had so far. It does give us some leeway when the general requirements don't make sense at all. So there you have it. I hope this helped you out with 250.122b. Like I said, it is kind of a tricky topic and a trippy topic for that matter. But anyway, hope you enjoyed the video. Hope you got something out of it. And please be safe. We'll see you next time. Thanks. Be sure to like, follow, subscribe, and ring the bell.